Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so today is our great pleasure to have Jeff Hinton to come back to our group again. Last year, he spent about 1 week with us. We got a tremendous amount of progress on some of the research that on deep learning, on speech that we have been pursuing afterwards. So today, you're going to hear some even more exciting ideas that he will talk about. So I'm not going to give out introduction about what he has, except to let you know that some of the things that he's doing is very exciting. And then now I'm going to give the floor to Jeff.
Thank you. First of all, I'd like to thank the speech group for giving me some money, and also Eric Horvitz for giving me some money. That was all very nice. I'm always open to more. I'm going to spend about a quarter of an hour explaining what deep learning is, and many of you here know this stuff already, so you should wake up after about a quarter of an hour. I'll then describe about a quarter of an hour describing how it's applied to speech, and about a quarter of an hour describing how it's applied to generating images that look like natural images, which nobody seems to be able to do. And then the very last part of the talk, I'll describe an amazing model produced by 2 students called James Martens and Ilya Sutskever that takes a string of 500 million characters from Wikipedia and learns how to predict the next character and does an amazing job of generating text after that. It does a job that's much too good, and I don't understand. I kept thinking there must be a bug, it must be cheating, but we'll come to that at the end. So back in the 1980s, people invented the backpropagation algorithm, and you have multiple layers of neurons, and you can learn the weights on the connections, and you can learn weights like this that determine what kind of a feature detector that is and what kind of a feature detector this is. And we thought we can now solve everything because we can learn multiple layers of nonlinear feature detectors. And it was quite good for quite a few things, reading checks, for example, but it had some serious limitations. And the main limitations were this. It required lots and lots of labeled training data, and back then that was very hard to get. The learning time didn't scale well for deep networks, and deep networks were the most exciting ones because they could learn lots of nonlinearities. And it could get stuck in poor local optima, which might be quite good, but it turns out you can find much better ones if you learn a slightly different way. So we're going to try and overcome the limitations of backpropagation by learning a generative model instead of a discriminative model. That is, instead of learning to produce a label given an image, we're going to start by learning to model images. And we're going to try and build a multi-layer generative model, and that will have lots of features in it for generating images. And those features, which are learned to be good at generating images, we're then going to use for discrimination. And many of them will be irrelevant, but the ones that are relevant should be very good. And it turns out that's a much better way to do discrimination. So in a sense, we're going to try and learn to do computer graphics before we try computer vision. So the question is, what kind of generative model? And now we're going to make a bunch of apparently bizarre decisions. The historical justification of them is I gave up on this problem, went and worked on something else, and then discovered the other thing I was working on was the solution to this problem. So we're going to learn a generative model that only has one layer of hidden variables, which doesn't seem very good if we want to learn deep networks. What's more, we're going to make it an undirected generative model. That is, it's going to have hidden variables, which are going to be features, and visible variables, which are going to be pixels. But the relation between the two is symmetric. So pixels cause features, but also features cause pixels. And there's nothing really to distinguish the features and the pixels in the model. And we're going to make everything binary. They're all going to be Bernoulli variables, which seems like a bad idea if you want to deal with the real world. So we'll make these 3 bizarre decisions, and then we'll gradually unpick them. So the units we're going to use are these stochastic binary units. They get some total input, which is a bias plus the weighted input from the states of other guys times the weights. And they output a 1 or a 0 probabilistically. And we're going to arrange them in a bipartite graph where you have visible units where you put your observations, hidden units where you're going to learn features, and you have undirected connections. This thing's governed by an energy function. It has the nice property that if you give me a visible vector, I can immediately write down the full probability distribution for these hidden units. They're all conditionally independent, and I can compute the probability of each of them. And since they're independent, that gives me the full distribution. And I can sample from the distribution easily. So it's very good for doing inference. And initially you think it's going to be hard for learning, but it turns out there's a quick way to do learning. So in that restricted Boltzmann machine, there's two conditional distributions that are relevant. There's the probability of a hidden unit j turning on given a visible vector, and that's just the logistic function of the bias of j and the sum of the inputs that it gets from the visible units that are on times the weights on the connections. And then there's something which is just the same the other way around, which is the probability of a visible unit turning on given a hidden vector. That's what you'd use to generate from a hidden vector, and it's just the same thing the other way around. Now, using those two conditional distributions, you can do the following. You can put a visible vector in here, and now you can compute the probabilities of all these hidden units, and then pick their states according to those probabilities, so you get a binary vector. And then you can do the same here, so now you're reconstructing that visible vector from the features, and you just keep going until you've forgotten where you started. That's called the stationary distribution. And you measure the pairwise statistics of a pixel being on and a feature detector being on here, and you measure the same pairwise statistics there, and that difference in pairwise statistics is exactly the derivative of the log probability of this input vector here with respect to the weight on this connection. That is, you can take this model and you can run it backwards and forwards like this until it's generating fantasies, and you can look at this distribution. That's the model's distribution. And if I show it some vectors here, what I want is for the model to have the same distribution as the data. So if I generate from the model, I get the data distribution. And this is the derivative of the probability that the model will generate this visible vector here. And it's a nice simple form. It depends only on things to do with that connection, even though this derivative actually depends on all the other weights in the network. But that dependence shows up in these correlations here. Now, that learning algorithm, you have to decide how long to go for. And after a very long time, after 17 years, in fact, I discovered you don't actually need to do that. You just do this. You go up, and you come down, and you go up again. And you take this difference. Now, this isn't following the derivative of the log probability of the data. It's not maximum likelihood learning. What it's doing is it's taking the data, it's representing it with the features, it's then reconstructing the features with something the features would like to believe in. So that this is the data polluted by the beliefs of the model, but only slightly polluted. And you're measuring statistics with the data and statistics that's been polluted by the model's beliefs, and you'd like them to be the same, because then your model isn't polluting the data. So intuitively, you take this difference and do learning, and hey, it works. It's following the gradient of another objective function, almost. So it's not doing maximum likelihood. It's doing something much closer to following the gradient of this other objective function, but it's not even doing that. But the main thing is it works, and it's quick. So we can train a restricted Boltzmann machine like that, and we can give it binary data, and we can train it to learn lots of features that represent that data. And once we've finished training, if you run this model backwards and forwards, it'll produce stuff that looks like the data. The reason it's interesting is because we can now stack these things up. With these undirected models, it's very easy to stack them up. What you do is you first train one of these restricted Boltzmann machines, and it learns a layer of features that model the data. You then take the activations of those features, and you say, that's data now. We've learned the first layer. Let's learn another layer that models the correlations of those features. And we keep going like that. And we can guarantee that, unless you've already got a perfect model, each time you add another layer, you improve your model of the data in the following sense. There's a variational bound on how well you're modeling the data. And if I add another layer in the right way, that variational bound is guaranteed to improve. So there's something that's getting better when we add more layers. And that's our kind of security blanket. There really is underlying in the math, there's something that's improving as we add more layers. We now violate all the assumptions you need to prove that. This is sort of normal practice, right? And then we just get on and we learn lots of layers. With this sort of security, behind all this, there's something sensible that we're doing. And now we're just getting on with it. So if, for example, we had some data here, and we learned a layer of binary feature detectors, and then we took the activities of those when they're being driven by data and learned another layer, and then we took the activity of those and learned another layer, we then have these three restricted Boltzmann machines, and we want to put them all together into one model. And what's surprising is the model that we get is not a great big Boltzmann machine. That's what everybody thinks, and it's not. The top two levels is the last restricted Boltzmann machine. So that's a little Boltzmann machine, a bipartite undirected model. But when we put them together, what we're really doing is this lowest level model has a sort of prior here, and we're substituting this high level model for the prior, and we keep doing that. And we end up, the only thing we keep from the lower level model is the P of V given H. And from this model, the only thing we keep is the P of this H given that H. And so we end up with a model that's a restricted Boltzmann machine at the top. That's like an associative memory. And underneath that, it really is a belief net. It's a directed model. If you want to generate from this model, you go backwards and forwards here forever, and then you go clunk, clunk once. And then you can see what the model believes. Okay, so that's why it's called a deep belief net. It has this undirected bit at the top, but all the layers below are belief net kind of stuff. So we accidentally discovered how to learn deep ones of these. You work on a different problem of learning a restricted Boltzmann machine, and then after I'd realized you could stack them and do nice things, eventually a very smart student called Yi Wai-Tei realized that's really what you're doing, and you're producing a belief net this way. Now, after you've done all that, you can then throw away the belief net you produced and say, really, I've produced all this stuff. When I view it as a belief net, the connections go this way. But it's also a belief net in which I can do very fast inference by using the connections backwards. And what I'm going to do now is just treat it as a feed-forward neural network, a good old-fashioned feed-forward neural network, that I just happen to have pre-trained all the feature detectors without looking at the answer. And that's good, because that means I don't need the answer to pre-train all these feature detectors. If I've got lots of unlabeled data, this is great. So having learned all that, all these layers of feature detectors, we then stick our label units on top, and then we just use standard backpropagation to fine-tune it. And this works quite a lot better than standard backpropagation if you don't do all this pre-learning. So one reason it works better is it goes faster. Once you turn the backpropagation loose, you get sensible gradients, and you're just doing a local search. You're sort of fine-tuning it. It's not really changing the feature detectors much. It's just changing them a little bit to get the category boundaries in the right place. It also generalizes much better. And that's because most of the information in the feature detectors, in all those weights, comes from trying to model the input. And the input's typically a big, rich thing with lots of information in it. You have about 10 to the 14 weights you need to set. And you only live about 2 times 10 to the 9 seconds. So you need to be setting about 10 to the 5 weights per second. Your mother would have to give you at least 10 to the 5 bits per second of instruction to do that by discriminative training. And she doesn't. The only place you're going to get 10 to the 5 bytes per second, which is what you need, is the sensory input. That's the only place where there's enough information to determine all these parameters. There's not enough information in the DNA.
But it's not, you're not born tabular, right?
Right, but that's why I said there's not enough information in the DNA. Okay? That's only 3 billion bases or something. It's negligible compared with what you need. Okay. So because most of the information in the weights comes from trying to model the input, it generalizes much better. You're not limited by not having very many labels. Now, one thing wrong with it was we started off developing it for binary data, and most of the things you want to apply it to, like speech and vision, have real values. So we're going to modify the model just slightly. We change the underlying energy function, and the result of changing the energy function is that the rule for setting the states of the hidden units is it's basically just the same, except that the activity of a visible unit needs to be measured in units of its standard deviation. We're going to have linear Gaussian visible units, just like in factor analysis, and they're going to have their own noise levels. That's the standard deviation of the noise level of a unit. That's the measurement noise in factor analysis. And you have to measure the V in units of standard deviation, because that's the sort of log probability stuff. Then when you come down again, it's quite different, because these are linear units. So the way you determine the state of a visible unit, that shouldn't say P of V equals 1. That should say P of V, sorry. The way you determine the real value state of a visible unit is it's a Gaussian. The unit learns its own mean, but then the top-down input coming from the hidden units causes an offset to that mean. And the magnitude of the offset, again, depends on the noise in that visible unit. If it's very tight, you need a lot of top-down input to move it over. If it's got a very sloppy high variance, you don't need much top-down input to move it over. And then there's this noise level in the unit. So those two conditional distributions go like that. And now we can learn with real values, where this is a real value now. So we applied it to speech recognition. Two of my grad students, George Dahl and Abdul Rahman Mohammed, applied it to recognizing speech on the TIMIT database. And normally when you do speech recognition, you have hidden Markov models that model the sequence of phonemes, and you have to relate them to some representation of the acoustic input, which is typically the Mel-Kepstrel coefficients, which a long amount of development in speech recognition said were good things to use, plus their first and second derivatives. And then what you do is each node in the hidden Markov model has a Gaussian mixture model for trying to fit these guys. And we're going to replace that by something that goes in the other direction. It's going to be a feed-forward neural net. And this was done in the late 80s or early 90s by people like Nelson Morgan and Tony Robinson and Yoshua Bengio. We replace it by something that takes the Mel-Kepstrel coefficients and tries to predict the probabilities of these states of the hidden Markov model. Okay. But we used a very deep net. So all the people doing that use fairly shallow nets, and it works better if you use a deep net. In fact, George discovered the net that works best is, here's your input representation of 13 Mel-Kepstrel coefficients plus their first temporal derivatives and second temporal derivatives. And he then puts that into 2,000 binary hidden units. That's a lot. Then another 2,000. So there's 4 million parameters right there. Between every pair of layers, there's 4 million parameters. And he pre-trains all this stuff. And the thing that worked best was 7 layers pre-trained like that. Then he puts 183 labels, because there's 63 phonemes, and then each one has 3 hidden Markov model states, and you're trying to predict which hidden Markov model state. That's not pre-trained, but notice that's far fewer parameters. And then you just fine-tune it with backprop. And at the point at which he did that, the best result on the standard TIMIT database was 24.4% phone error rate, and he got 22.2% phone error rate if you count the silences, which everybody does because they're easy. Initially, we didn't count the silences, and we were only doing a little better than this. And then we discovered everybody else counts silences, so we did too. So that was nice.
Is it 24.4 Robinson's number?
No, that Robinson's number would be about 26.3 or something like that. That was the best recurrent net. This is actually averaging a whole bunch of different models. Now, at about the same time as we did this, IBM started taking its large vocabulary speech stuff and applying it to TIMIT. And if they do it speaker independent, they get a similar result to this. It's not better, though. And in a minute, we're going to make this better. So there's something... Well, the first thing is, people say, but things that work on TIMIT don't work on big vocabulary. Does this work on big vocabulary? So George came here and working with the Microsoft people on Bing voice search. He tried on big vocabulary. And if you train on 24 hours of speech, they get 62% correct using a Gaussian mixture model, and the DeepNet gets 70% correct. Now, this isn't entirely fair, because the Gaussian mixture model you can train on much more data. If you train it on 1,000 hours of data, which is what they actually do, you get performance that's very comparable with this. There's all sorts of little things you can change, but it's sort of at about this level, maybe slightly worse, which suggests that if we could train this thing on 1,000 hours, we'd wipe them out. But at present, we can't, and we're thinking of ways of trying to train it on 1,000 hours. There's one embarrassing thing about that nice model, which is that in the underlying math, you have these visible Gaussian units that have their own measurement noise level. It's sort of the residual noise. That should be the residual prediction error when you try and predict what they're up to. And we took the data and we normalized it so it had variance of 1. But to learn this model, we also used a residual noise model of 1 with a variance of 1, which is crazy. We're saying you can't predict the data at all. Now, it works, but when we tried actually learning this, it didn't work at all. And I spent like about a year trying to understand what the hell was happening, why we couldn't learn it, and throwing more and more graduate students onto the funeral pyre, you know what I mean? And you really can't learn it. Even if you get hyper-Bayesian about it, it's still very tough to learn it.
But MSR, Cambridge, they have a vision group. They came over to discover.
Yeah, they have a complicated way of trying to do it, right?
Was it successful? Or?
And it was somewhat successful, but they didn't really understand what the problem was. And we've now solved the problem. We can learn it much better now. And so I'll show you what the problem is. Remember when we got the two conditional distributions? We're dividing by the standard deviation of the residual noise here, and we're multiplying by it there. So the the bottom-up effects, you divide by it, and the top-down effects here, you multiply by it. So if you draw a picture of what's happening, the effect of changing this standard deviation is to, if you make this small, it effectively makes the bottom-up weight very big, and it effectively makes the top-down weight very small. So suppose we make it a tenth, which is about the right level. These weights are 10 times too big, and these are 10 times too small. And the result of that is these hidden units all get saturated very early and have no flexibility to learn left. And these guys never get enough top-down oomph to actually drive them very far from their means. So it sort of under-reconstructs all the time. And that's sort of an embarrassing problem. And there's a simple way to fix it. What we're going to do is we're going to have an infinite number of hidden units. This is actually good for getting NIPS papers accepted because you have to have infinite in the title. So we make infinitely many copies of each binary hidden unit. They all have the same weights and they all have the same bias, so there's no more parameters. But they have offsets in their biases. So their thresholds get progressively higher like this. And so if you provide this thing with some total input x, the ones way up here won't actually turn on, so you don't really need infinitely many. But you don't know in advance how many you need because it depends on how big x is. And now, if you make x 10 times bigger, 10 times as many of these will turn on. And so now you're in good shape. Because now, if you make this input 10 times bigger, you get, sorry, if you make this be a tenth, that makes the bottom of input 10 times bigger. 10 times as many of these turn on. That makes the top down 10 times as big, which cancels out that tenth there, and so we're back in business. Of course, we do need this infinite number of these binary units.
Now, can you fix the energy function to begin with to reconcile that difference to begin with?
Well, it amounts to doing this.
It's the same thing.
So it turns out that if you take an infinite number like that and you compute this infinite sum here, that thing is exactly the same as this thing. That is, in the limit, as your sort of steps in your threshold get very small and you scale everything down, they become the same. But with steps of 1, they're so accurately the same, if you plot the two, you think you forgot to plot one of them because you only see one line. So it looks like this. So basically, we can model those guys very well with something like this. And we can model this with a sort of linear threshold thing with some noise in it. And it's a pretty good model of this if you make the noise level depend on the logistic of this. So when this is big, the variance of the noise is 1. When it's big and negative, there's no variance in the noise. And round about here is where you're getting you get this curve thing by adding noise, basically. So in MATLAB, that's what we actually do. You say the output of one of these units is the max of 0 and x plus some Gaussian noise whose variance is the logistic of x. So that's what you plug into your program. And now you've got something efficient again. We call these rectified linear units. And that works really nicely. So then we can turn it loose on speech. And in fact, now that we know how to learn these models with binary hidden units, well, these rectified linear hidden units, and real-valued Gaussian visible units, we can learn our own representation of speech. I mean, people do this Fourier analysis, and there's a lot to be said for Fourier analysis, except that speech isn't really cyclic like that. It makes all sorts of assumptions that aren't quite true. And people have developed these Mel-Kepstrel coefficients. But Mel-Kepstrel coefficients were developed when people had small computers, and the main problem was to get rid of most of the data so that it would fit in your computer. And also to blur it in a way that blurred together things that should be classified together. But we've got much more powerful models now, and we don't really want to blur it. We want to see what's going on. So we're going to actually do something that sounds crazy. We're going to take the raw speech wave, 100 samples from the raw speech wave, and this is 120 of these rectified linear hidden units, and we're just going to learn how to model a tiny little piece of raw speech wave. This is going to be 6.25 milliseconds at 16 kilohertz. And we train it just the way we trained these standard Boltzmann machines, and we're going to get some rectified linear features here. And the question is, what are they going to look like? So you get a lot that look like what you expect, which are little sort of wavelet-y things. You might expect to find things at different frequencies like this. But you also get guys like this. And this guy's kind of cute. He's got one low frequency here, and superimposed on it, he's got another high frequency. And that's sort of right there in the front end of the system. And so if you take his Fourier transform, it looks like this. It's got lots of energy here and lots of energy here. And that's actually detecting a vowel, and those are the first two formants. So if you take real speech data, a lot of the time people are saying vowels, and so the data has a lot of these things in it where you have two formants, and what's more of a roughly constant separation. And so this thing just goes and detects them directly.
So if you were to use the conventional Bernoulli unit, you wouldn't be able to get this?
No, you can't get this. You have to learn the variances to get this. You have to learn type variances. You basically have to learn a proper model to find these things.
Even if you use this trick that you showed us last year?
The trick I showed you last year is a kludge before I'd really figured out what was going on. And next year I'll probably say this was a kludge. Okay, so now we can apply it to Timit, and we do slightly better than Mel-Kepstrel. Yeah.
A couple of things. I assume you don't actually use the Fourier transform. That was just to show on the slide. You're just using the features directly.
Yes. The Fourier transform there was just for analysis of what these features represented in conventional terms.
One of the points of the Kepstrel is to remove the pitch information so that it's now you're frequency dependent with what you just learned.
Absolutely.
Are you going to do the equivalent trick, make it homomorphic to remove that information?
Nope.
Okay.
Our idea is you don't want to remove information, you want to model it. And if you've got lots and lots of layers of features and a big computer, you can afford to model all sorts of stuff that might turn out to be useless because you're building a generative model from which.
But as long as you go across multiple speaker types, multiple frequencies, then you'll learn the features that are necessary. Okay.
So now what we do is we actually now advance this window by just one sample and do the whole analysis again. Okay, so we're not going to lose much this way. We get a hugely over-complete representation, 120 times over-complete. Then what we do is we look at these outputs, look at the output of a hidden unit on all these different little windows that are advanced by one sample, and pool its output over 160 frames. So you're really saying, did this feature get active anywhere in there? But we make these pools overlap. And now we take that stuff and build more hidden layers on top. And hey presto, we do a bit better than Mel-Kepstrel, about 1% better. So a standard speech recognition system starts with Mel-Kepstrel coefficients. It then uses a Gaussian mixture model to relate these to the underlying hidden Markov model. And you can predict what I'm going to try and do next. That's going to be the last part of the talk. We don't know how to get rid of these yet, but we will.
MFCC is like SIFT feature in vision.
Yes, not quite. Because SIFT features come with accurate poses and things. Okay, so now I'm going to switch to natural images. And we're going to try and apply the same technique to modeling image patches. And images consist of smooth stuff with sudden discontinuities to first order. That's what people find so hard to model. If you just model the Fourier spectrum of images and then generate from it, you get clouds. They don't look like real images. So here's some images. And this image and this image are very similar if you use a color histogram. And if you do a template match of these images, they're pretty similar. In most places, they match very well. But this image is really more similar to that one. And if you sort of had to remember which two are similar, these are the ones that are really similar. And so it's not the mean intensities that matter. It's which intensities are the same as which other intensities. That's what matters. And that's the covariance structure of the image. Now, you can, of course, fit Gaussian mixture models which learn in the parameters certain covariance structures. But the thing about images is every new image has its own covariance structure. And so we want something that's dynamic that will model the covariance structure of that particular image. And that means we want some basis functions for covariance structures. And we want to represent this image as you've activated all these covariance basis functions, and they, between them, produce an image with this covariance structure. We also want to model the means. And so we're going to have a model that looks like this. Here's your pixels. Here's your standard. So this would be a standard sort of Gaussian binary RBM. And you might want to replace this with these rectified linear units. But actually, in this work, we normalize the image patches, so you don't really need those to begin with. And then this is the bit that's going to model the covariances. What we do is we take some linear filters, things that are going to look at the image, and we're going to now square their outputs, and we're going to send them here. And then these units are going to be units that are always on unless they're suppressed. And we're going to make sure these weights are all negative. So the interpretation of this is, this unit here is saying, my bit of the image is nice and smooth, so you win by B. You get a bonus of B because your bit of the image is nice and smooth. This filter here is going to learn to detect things like an edge. And when there's an edge there, it's going to activate this guy. It's going to provide input here. And now that's going to suppress this guy. And so you don't get this bonus. But as this gets more and more active, once this guy's been turned off, it doesn't cost any more. Once you've decided it's not smooth after all, you don't get a bigger and bigger penalty as the edge gets stronger and stronger. And that's what you want. That gives you your heavy-tailed property. I went over that very quickly, but that's the sort of basic idea. And now we're going to train this thing. And we use a training algorithm that's basically this contrastive divergence algorithm. There's all sorts of variations to it to make it work for this kind of circuit. And they're all in a NIPS paper, in the upcoming NIPS. And I don't have time to go into them here. But I want to show you what happens when you generate from this. If you learn on image patches, here's what image patches look like. And here's samples from the model. And they look quite like image patches. They have this property of being locally smooth and with sudden outbreaks of structure. So, this looks like the same kind of stuff as that. Whereas clouds produced by a Gaussian model don't look at all similar. Marc'Aurelio Ranzato, who did this work, then wanted to apply it to big images. So what you have to do then is you're going to model a patch and you're going to replicate it across the image so you can model big images. But if you've learned a filter and you replicate it across the image with a small stride, that filter will overlap with itself. That's what happens in a convolutional neural net. And that's a disaster. Because where it overlaps with itself, in order to have high representational capacity, it wants to be orthogonal to itself. It wants these two outputs to be different. And so the filters try and learn to be orthogonal to themselves in all possible overlaps. And the thing that's that is high-frequency noise. And so they learn high-frequency noise. And there's a method called a field of experts that took our earlier work and put it in a convolutional net. And they learned high-frequency noise. And surprisingly, that works quite well. But you can do much better if you don't allow a filter to overlap with itself. So what we're going to do is we're going to tile the image with a filter. You learn a filter, you move it over by the width of the filter, and then do another one. So those are replicas. But then you have lots of offset tilings of the image.
Why didn't you have the same problem in the speech case, just a one-dimensional image? You did the overlaps?
We probably did, and we can probably do better. This is very early work. So we're going to have a red tiling of the image. So there's a red tile, and we tile the image with these red tiles. And for each red tile, we learn something like 64 filters. And then we're going to have another tiling, the blue tiling, which is diagonally offset, so you minimize block boundary artifacts. And we're going to learn 64 filters for that, and so on. And here's some of the covariance filters learned by the red tiling. And you can see they're picking up on edges and things, and occasionally a bit of high-frequency noise. But edges of different frequencies is what they really like. And so we learn lots of those. We also learn mean filters, again using tiling. And now that you're learning the covariance filters, you know what should be the same as what. So in order to model the intensities in the image, you don't need to actually worry about where the edges are. You know how you can do watercolor by having a sort of blob of color and then spreading it out until it hits the edges? Well, that's what this model does. Its model of the mean has these rather fuzzy models that it's sort of bright round here. But when you combine that with the covariance filters, if there's an edge here, it'll spread that brightness this way, but it won't spread it that way. So it's this sort of watercolor model of an image that you have a color wash and then these edges that it gets slaved to. And that just comes out in the math. So when you generate from it, here's a big image generated by using just the second order, the power spectrum. And it looks like that. One of the best models of images is the Gaussian scale mixture. Notice it's a mixture model. And it's deciding for each little bit of image what's going on there and what frequency it is, what spatial scale. But if you generate from it, it produces something like that. It's a good model of images, but hopeless as a generative model. If you take the field of experts model, that's this model here, and that's like the model I described, but it's only using the covariance units. And also, it's overlapping the filters. It's not tiling the image. And that produces something that's sort of better than this, but doesn't have sort of areas with edges. It's quite a nice texture model. If you take a pairwise MRF, it produces something like that. If you take the model that Marc'Aurelio developed, it produces something like this. So at least you're getting sort of regions with edges. This looks a bit like a Henry Moore sculpture. Here's another sample from the model. Okay. So these are samples that are a lot more like images than what people could produce before. Well, I mean, I should hesitate. From a parametric generative model. There's many, many ways to put images together by stitching together little pieces of other images. But from a parametric generative model, it's very hard to get things that look as much like images as that. Here's some more sample. Oh, okay. So now what we do is we stick a hidden layer on top. And if you stick a hidden layer on top, and then take this restricted Boltzmann machine on top and go backwards and forwards in that, and once that's settled down, you now generate the image using the lower layers, you get something that looks like this. I should have got more samples of this. That looks like a really bad photo that someone took, right? It's out of focus, and you can't tell what it's a photo of because it's such a bad photo. But at least you could mistake that for a really bad photo. And you couldn't have mistaken any of the others for that. If you use more hidden layers, it's not clear to me whether this is better, but you end up getting stuff like that. So this is with 3 extra binary layers. You go backwards and forwards in the top 2 layers, and then you generate. And actually here, the top 2 layers don't have that many units. What you can do also is you can put a real image in there, infer up to the top layer, and then regenerate from the top layer of binary units. And it looks just like the real image, but a bit blurry. So that top layer can represent all that structure. It's a sad fact. We haven't managed to show that it's good for denoising images. That would be the killer thing to show. But it is good for generating images. Okay. I might have one more of those. Yeah. There's another sample from the model with 3 extra layers.
For enhancement, when talking about denoising, species people do the same problem.
Yeah.
So according to this approach, it would be to train the model.
You train the model,
and then
you then take the image and you say, follow the gradient of the log probability of this image. If you've got a probabilistic model of an image and you can compute the log prob up to an unknown factor, up to an unknown additive offset, you can follow the gradient.
Image model first, right?
You would train on all images.
Okay. Now,
of course, if you want to denoise a certain class of images, you train on that class and you'll do much better. Okay. One final thing we can do is take that model we developed for, the Marc'Aurelio developed for images, and George just took his code and applied it to speech. And so this was actually frames of filter bank outputs. He didn't put in the deltas and delta deltas, because those are for capturing the temporal correlations, and we can model correlations now, so we don't need them. And he tried this mean covariance RBM as the front end, and then just multiple layers after that, and trained it up the same way as before. And now it does sort of quite a lot better. And this is the record for speaker-independent phone error rate on Timid. We don't know whether that'll generalize to bigger databases. George found it hard to get it to work on a bigger database. We now have a version that's much easier to get to work, and we're working on showing that it'll work on large vocabulary.
On the image one, have you done any classification statistics yet?
Yes, Marc'Aurelio's done classification stuff. The place where it really wins is if you take a face and you obscure a bit of the face, and you tell it that that's been obscured. So a face with some object in front, and you know there's an object in front. So you know you don't use those pixels, you know that those are unknown pixels. And now what you do with the generative model is you fill that bit in and then recognize, and that does much better than any other technique. That's sort of semi-cheating, but it does much better, for example, than if you fill that in by linear interpolation and then recognize. And now I want to get to something completely different. The other thing that was disappointing back in the 80s about backpropagation was there was a particular version of backpropagation that was clearly the exciting version, and it wasn't this multi-layer stuff. If you take a recurrent net like this, I suppose it takes one time step for this guy to affect that guy via this weight, I can explode it in time like this, and so this effect here, W2, is happening there, it's also happening here, it's also happening here. So by tying these weights together, I can make a feed-forward net like this be equivalent to a recurrent net. And if you tell me that this guy should have been in a particular state, I can backpropagate the error and I can train up all these weights, keeping these ones the same as each other. And in particular, I might say, I'll take some units and make them the input units, so I'll provide input here. I'll take some units and make them the output units, and I'll have desired output here, and I'll have some hidden units, hopefully more than that. And so now I can have something that takes a stream of input and spits out a stream of output with a little time delay. It needs sort of 2 steps to get there. And that thing ought to be able to learn wonderful things. It ought to be able to learn sort of little programs, and lots of little programs operating in parallel that between them manage to compute the right answer. And so I was really excited by this. When I realized that backprop would do this, I thought, we really got it now, because we can learn in this big net, we can get it to behave like all these little programs. And the problem was you couldn't train this, particularly if you try and train it over, say, 100 time steps. The error derivatives either die or explode. And that's because a net like this tends to have attractors. And because it's got attractors, between 2 attractors, there's a sort of bifurcation point. If you start at that bifurcation point, you get an infinite derivative, and anywhere else you're going to get a near 0 derivative. So the derivatives tend to be infinite or 0, which isn't good news. And so people gave up on these, essentially. Tony Robinson used these for speech, but later on there was some excitement, and then people basically gave up on these.
They couldn't reproduce the result. Yeah. It worked once.
OK. I bet you we could reproduce it now.
Well, not using RNNs.
Yes, using RNNs, because we can train them much, much better. So 2 of these graduate students, one in particular, James Martens, thought, well, maybe the problem with these is just you're not using a good enough optimization technique. And over the years, optimization people say, you should use this technique, you should use that technique. But they're not willing to put in 6 months to make their technique work on neural nets. And James Martens took one of the best techniques and put in 6 months making it work on neural nets. And boy, does it work. It can follow these derivatives over hundreds of time steps now. So basically, you want to use curvature information to decide which direction to go.
But what if you just use the standard pre-training for a fixed number of length?
It's very hard to pre-train these guys because the weights are shared, remember.
I see. Okay, so
we're working on trying to do that, but it's not trivial to figure out how to pre-train them.
Oh, is that because of the number of depth?
No, it's because the weights at every layer are shared, so you can't separate, you can't modularize it in the same way.
Have you compared your results to Ristos at University of Texas?
We compared to some Schmidt-Huber things. Anyway,
Okay.
I'm going to let the results speak for themselves. So instead of using quasi-Newton, which is approximating the curvature matrix and then doing a line search to find how far to go, you use a different approximation to the curvature matrix. You use the Gauss-Newton approximation, which is guaranteed to be positive definite. And you put a huge amount of work into getting a good approximation. It's not the full matrix, because that's hopelessly large. But you're very interested in like the 100th eigenvalue, which is thousands of times smaller than the leading eigenvalues. And you want to get it right, because there's these directions that have very, very low gradients, but even lower curvatures. And it's the ratio of the curvature to the gradient that says how much wing you can make. And so in among this, there's a conjugate gradient line search that's used just for getting a good approximation to the curvature matrix. And what's more, the literature says use 5 steps of the conjugate gradient line search. And James discovered actually 250 steps is what you need. And there's all sorts of damping goes on too to do with trust regions and all that. And he put a lot of work. There's an ICML paper that shows it doing impressive things on toy problems. He's made it work better since then. And another student, Ilya Sutskever, has now applied it to predicting the next character in a character string. I'm not going to talk any more about the method. You can read the ICML paper. There's something very nice about working with characters, which is that's how the web comes. It's just characters. If you try and work with words, you have to stem them. If you're doing Finnish, you've got a nightmare because there's all these morphemes, things like morphemes. Even in English, there's problems. So there's all these prefixes and suffixes, and you don't know whether to strip them off or leave them on. There's things like New York. You don't know whether to make that 1 word or 2 words, because sometimes it's 2 words. And there's all sorts of subtle effects that you don't know, but are there in English, and you'd like to pick up on. Like, words beginning with SN typically mean something to do with the upper lip or nose. So there's things like snot and sneer and snide and snarl and snap. There's lots and lots of them like that, far too many to be chance. Now there's things like snuggle, which doesn't mean that, but snuggling leads to snogging, and there you go. And then people always come up with, there's one exception people always come up with, they say snow. Snow's got nothing to do with the upper lip. If you ask yourself, why is snow such a good name for cocaine? It's the perfect name because it's white and it's to do with the upper lip and nose. There you go. I don't think that's a coincidence.
So this approach will automatically
Okay.
discover all this.
So the point is, that's a regularity of English, and this thing will learn that regularity. And a linguist doesn't even know it, most linguists. I think I got this from George Lakoff. So some linguists know it. Okay, so we're going to do a net that works like this. It's not your standard recurrent net, but it's quite similar. We're going to have 2,000 logistic units, and here everything's going to be deterministic. 2,000 logistic units that have real value states between 1 and 0. And the real values are important. If you mess with them too much, it doesn't work. And we're going to have another 2,000 units, which is the state of this at the next time step. So this is one time step. And we're going to make a character not provide input to these units, which would be the standard thing to do. We're going to make a character determine the transition matrix. So we're going to say what a character does is take some state and determine the transition matrix that gives it a new state. And one way it could determine the transition matrix is each of the 86 characters we use could have a lookup table that just says, I correspond to this transition matrix. But then you'd have 86 times 4 million parameters. And that's probably a good thing to do, but it's too many parameters. So what we're going to do is take that kind of 2,000 by 2,000 by 86 tensor, that 86-fold matrices, and we're going to factorize it. Just like PCA factorizes a 2D matrix, we're going to factorize a 3D tensor, and we're going to factorize it in the following way. We're going to have a whole bunch of factors, these little triangular things, actually 2,000 of them, which is confusing, but there you go. 1,999. Let's suppose we had that many. And each factor is going to work like this. If you think of it in how you program it, you take these states, you multiply them by the weights on these connections, so this is a linear filter, and now the character tells you what weight to put on that linear filter. So you take this linear filter, multiply it by this weight here, and then send that out along all these connections, where it gets multiplied by these outgoing weights. So another way of, and then that's the contribution that this factor makes. And you have lots of factors. So this character says, let's use a little bit of this factor. It's like cooking. Use a little bit, it really is cooking. Use a little bit of this factor and a bit more of that factor. And each character use different amounts of different factors. So, for example, similar characters, like vowels, might use similar amounts of the same factor. All of the digits use very similar amounts of different factors, because they all have very similar distributions. Another way of looking at it is take the outer product of this vector, and you'll get a rank 1 matrix. And then what a character is doing is building up a whole transition matrix by adding together weighted rank 1 matrices. And you're going to learn all this, of course. Once you've made the transition, you then try and predict the next character.
So is there a logistic function here as well?
And then there's a logistic function here, right? So this, from here is linear to there, then we put everything through a logistic here. Thank you. And then after you put it through the logistic, you try and predict the next character, and you get a distribution of the 86 characters. And then to train it, you look at the log prob of the correct character, and you backpropagate to try and increase that log probability. And you backpropagate through here and down through here, but also through here and down to the next character, and then through here and down to the next character, and you backpropagate for 100 time steps.
Well, the question is that if you don't use this factorization, since
It doesn't work as well.
Well, even if the web has almost infinite number of characters around for you to train.
Well, for the same number of parameters, it doesn't work nearly as well. That's what we know.
Okay.
It works a lot better when you do it like this. Because characters really are transitions from one state to the next state, so to speak. Okay, so the question is, if you train it on 5 million strings from Wikipedia, where each string's 100 characters long, so you can get it on the GPU efficiently. That's what Ilya Sutskever did. And you leave it running on your NVIDIA top-end GPU for a month, and then you come back and you look at what it's learned. We were hoping that it would learn some words, right? Because there ought to be words there, and it ought to learn some of them. And we're hoping it would learn common words. What we didn't expect is it would learn all the words, and it would almost never produce anything that wasn't a word, including very rare words. We were hoping it would learn a bit of syntax, but it learns lots of syntax. We were hoping it could balance parentheses that came near one another. It can balance parentheses that are like 40 characters apart, even if there's balanced quotes inside. And it's because it's not a hidden Markov model that's doing the remembering. It's got 2,000 real numbers as its state, as opposed to a 1 of n choice. So even if it was 2,000 binary numbers, you'd need a hidden Markov model with 2 to the 2,000 states to have as much representation capacity. And this has real numbers. So it's got a lot of capacity in those numbers. And so really, you want to see what it produces. So here is some text produced by just running the model. You give it an initial 10 characters, and then you say, predict the next character. I'm going to sample according to those probabilities. So occasionally I'll be picking something that thinks is pretty rare, and I just generate. If you always pick the commonest one, after a while it starts saying the United States of the United States of the United States of the United States of the United States. That's boring.
You know why? The number one page ranked value of the top eigenvector is United States in Wikipedia.
There you go.
Why?
Okay. Thank you. I thought it was just because it was the most important thing there was. But so here's some.
This one used the James Martens method for the training.
This one's using James Martens method.
That's why it requires a large.
Right. It generates this, right? And this is predicting a character at a time. So there's lots, and because it's trained on Wikipedia, you go search Wikipedia for these things. You can see if Wikipedia has well-paid types of box printer in it. And no, it doesn't.
How many of these strings did you actually go back and brute force look for the strings and see how many of them showed up in groupings?
I just did it informally. It's not been done properly. I did it informally thinking, oh, it must be getting this from Wikipedia. No, it's not there. It's creating these phrases. Most of them are created. And surprisingly, for example, the mansion house was completed in might be there. But I'll bet you it wasn't completed in 1882. I'll bet you it was some other year. It's very good at substituting years. Just occasionally it does something embarrassing, like saying 1882.3. But it doesn't do that very often. Normally it doesn't. And look at these phrases. Look, it is the blurring of appearing on any well-paid type of box printer. And it has longer range semantic stuff. So I'll bet you that the blurring and appearing in printer have something to do with each other. It knows you're talking about, printing and stuff. Okay, let me show you one more passage. Now, this was selected from a longer passage, and that was one of the nice bits. Here's another nice bit. So again, if you search for Opus Paul at Rome, I'll bet you don't find it. But we know that Opus and Paul and Rome have a lot to do with each other. And I'll bet you probably don't have Arab women's icons. You might have Arab women's icons, but you probably don't have now Arab women's icons and stuff like that. Look here. There's an opening quote. There's a closing quote. And they're like 40 characters apart. Normally, it starts paragraphs better than that. It starts with times or... Okay.
Yeah,
so it's producing good stuff.
So recurrent net, does it really have this capacity of learning long distance relation?
Well, look, quote and quote.
That's why I was so surprised. Because
Yes, everybody in the literature says, there's all these papers that say you cannot learn long distances with recurrent nets.
Any additional rules that
And
regularize?
the issue was, is it because of the optimizer you're using, or is it some eternal truth? And it turns out retrospectively, it's because of the optimizer you're using, and because you didn't have enough compute power to use the optimizer you need to use. Until these NVIDIA GPUs came out, we couldn't have done this experiment. That would have been, back in the 90s when people are saying you can't learn these long-range things, if we started the computation then, it would only be 1% done by now. Things are getting faster exponentially.
How deep was your net again? How many characters deep was
It only sees one character.
Yeah,
The rest
when
is in
you're
the hidden
training
state.
it,
It's infinitely long.
It's an infinite impulse response model. As a matter of fact, it never has a history of more than 100, but it could. It's infinite impulse response.
In model checking, for example, you can look at sort of finite traces of execution of the program, and by analyzing that, you can come up with invariants that will apply to longer segments of
So with English, you can do things like, it'd be fun to give this to an undergraduate linguistics class and say, figure out what it knows. You can type any string and it'll tell you how probable it is. Well, it'll tell you how probable it is given the context that you type ahead of it. You have to give it a context and then say, given that context, how probable is this string? So, for example, you can type a lion is a vegetable and a cabbage is an animal. And then you type a lion is an animal and a cabbage is a vegetable. And the second one is about 3 times as probable. Now you say, well, that's just associative knowledge. That's just kind of, vegetable went close to cabbage, so it sort of doesn't really understand. But if you say to people, what do cows drink? They say milk. They don't really understand either. They have a lot of associative processing going on. And this has huge amounts of associative stuff.
Can you test this with, longer and longer distance correlations to see if you really learn that, arbitrarily long quotations have to be balanced?
Yep.
And you also have like the quotes and the parens up there are not matched.
Yes, there's cases where they're not matched. It doesn't do it perfectly.
Have you put a supervised learning layer on top of this yet? Like teach it syntax, teach it semantics, labeled data?
Okay. So the problem is the labeled data corpuses are too small for this guy. But we did on there's a part of speech thing from Penn. And what you do is you train this net forwards, but now you're not training it to predict the next character. You're training it that when it gets to the end of a word, it should predict the part of speech. But that's unfair because it can't see the future. So you train one in one direction and one in the other direction. And when the backwards one gets to the beginning of the word and the forwards one gets to the end of the word, those two states are used to predict the part of speech. And the best systems get about 2.8% error, and this thing gets about 3.5% error. So it's good, but unfortunately it didn't beat the best systems. So we're not there yet, but it's pretty good. It really does, it can be trained to understand parts of speech pretty well. And those parts of speech, I can't do them. They're full of things like gerund. I don't know what a gerund is. Okay. So you can do little experiments on it. So here's some experiments. You make up a nonsense word. And then you type Sheila Thrunge and ask what the most likely next character is. And it says an S. And you type people Thrunge. And it says the most likely next character is a space. Now, you really need to do this for lots of pairs, because this is lots of statistics here. But I believe it understands that Sheila's singular and people is plural. I then thought I'd fool it, and I gave it Sheila, Thrunge with a capital T. And the first time I gave it that, it said Thrungelini del Rey. That's when I really started believing in this system. Because it's obvious Thrungelini del Rey is an exotic filmmaker with an Italian mother and a Spanish father who's currently in Switzerland. It knows a lot about proper names, a huge amount. If you give it your name, it'll know which order it goes in. If you give it 8 words, and you say, try all 40,000 orders and tell me what's most likely, the most likely order will be the sensible one. So it can do, most people doing natural language with machine learning are busy converting it into bags of words. We've got the inverse operator that takes a bag of words and converts it back to text, but only for 8 words.
Is that phrase in Wikipedia somehow?
Thrungelini del Rey, no, I checked. There's no Thrungelini del Rey in Wikipedia. There will be now. I sometimes call the program Thrungelini del Rey because I like the name so much. And I tried typing the meaning of life is, hoping to get 42, but 42 wouldn't have been that interesting because that's probably in Wikipedia. And you usually get garbage. You sometimes get quite interesting garbage. On the 6th try, I got this. And I thought that was amazing. The point is, it knows all these weird words. And so I don't know how to say what it knows. It knows a huge number of words. It rarely produces a non-word. When it does produce a non-word, sometimes you know it's a non-word, like interdistinguished. It produced that. That's a non-word. But ephemerable, ephemerable. Would you like to make your worst employees more ephemerable? And it produces parled, P-A-R-L-E-D, which I'm fairly sure isn't an English word, but it really could be.
Parlayed?
Parlayed is, and parled, you know what it means, almost. It's got lots of syntactic knowledge, but it's not in clean rules of any kind, and it's all mixed up with the semantic knowledge. So it has no problems with things like budge. You can have things that won't budge, but budge goes with a not, okay? And budge doesn't, you don't have things that like to budge. You have things that won't budge. And that's no problem for this kind of system. It only produced Wittgenstein once in the text I've seen it produced, and that was soon after it produced Plato. So it knows that those guys have something to do with each other. I'm finished, I think. Yes.
So if you were to use the old style training for recurrent network, like Tony Robinson style, probably will produce all the garbage.
It won't work very well. If you want to see how badly it works, look at Jeff Ellman's paper on it.
Yeah.
Okay.
Yeah.
So you mentioned that having the space of reals is a much richer representation than binaries. So is it worth then going back to all these image and speech problems and using stacked RVMs of all linear units or real units rather than binary?
No. And the reason is this. This was a deterministic model. Those models are stochastic generative models when you're doing the training. And if you force the hidden units to be binary, that's an incredibly strong regularizer. If you allow them to have real values, it doesn't model things nearly as well, because they use those real values, right? If they're forced to be binary, if I force a feature to be binary, it better be a sensible feature, so when I turn it on, it does something sensible. If I allow it to be real valued, then you can have a whole bunch of them with different real values, all conspiring to produce something by this guy cancels out part of that guy, and that guy cancels out a bit of this guy. And it overfits terribly. So I've tried using real values in these other nets, and it doesn't work nearly as well on the whole. Although these rectified linear units work, so maybe real values with some noise in are a good idea. But you need to put noise in to regularize it.
So is there any thinking about adaptation for this model, like giving Bill Gates speech for 2 lectures, and then to adapt the model, and they can...
Okay, so this kind of model, you can very easily do the following. You take all its parameters, and you freeze them. Okay, so it knows what it knows. You then have a whole new set of parameters, and they have the property that they learn fast, and they have a huge amount of weight decay. So they hate being away from 0. So they'll learn a little overlay on the model. So you could learn the Bill Gates overlay on top of Wikipedia. So now it'll produce stuff that it's got all its background knowledge in there, but it's going to overlay it to be much more likely to produce words like Microsoft and profit and stuff like that. And charity. Better be careful here. So you could do that for Shakespeare, for example. There isn't enough Shakespeare to train this. But you could train it on the whole of the New York Times, or something like that that's basically English. And then on top of that, you could train it on Shakespeare. And then it should start producing stuff like Shakespeare if you make the sort of Shakespeare overlay. And I think that's the way to do it with smaller corpuses. And in fact, I have a name for the paper when that works. And the name for the paper is going to be, It Only Takes One Monkey.
Actually, next, I would do what Sandia did for machine translation. I'd take the Bible and train it in English, train it in another language of your choice, separate model, and now use, because they're perfectly labeled against each other about which sentence is which sentence, and put them against each other to do automatic machine translation.
So basically then learn the mapping between the hidden states. Right.
And now you can put English in one end and get Italian out the other end, or vice versa.
Can I use Das Kapital? I think that's translated into lots of languages.
Bible's just a big corpus, that's all.
I guess I didn't quite get the whole thing. To train these two things, how do you get...
Well, now then you supervise learning between them. So
the hidden state, you see, at the end of, when you get to the end of a sentence,
Right.
the hidden state contains lots of information about what was in that sentence, plus previous sentences, plus contextual information. And so if you train on English and you train on French, and you have one-to-one sentences, like Hansard, then those hidden states better have something semantic to do with each other.
Okay.
And so now you try and learn the mapping separately. Some mechanism that maps things into other things, maybe a neural net.
Sandia used eigenvectors for this, and they just basically were able to do 50 languages where they could throw something in and get something back out, provided the sentence was something close to something in the Bible, yes. But they were not able to get down to this level in terms of the letter level and the predictive next. I'm wondering if you can apply this.
My internal model of what's going on could be completely off. Is you've got this 2,000 dimensional real valued space, so you can afford to put lots and lots of little attractors.
Exactly.
But that makes it seem very unlikely to be able to map the almost random distribution of English attractors to the random distribution of French attractors with any kind of a low-dimensional mapping.
The hope is some bits of that 2,000 dimensional vector will be remembering that there's an open quote and an open paren. Just a few bits. Other bits will be remembering that we're in the past tense. Other bits will be remembering that it's plural. Other bits, this was in the ideal world. Other bits will be remembering that we're talking about sort of pre-Christ stuff.
But why do you think
And
it would sort of...
And the semantic bits should map to each
Well,
other.
the semantics should match, that's the point. And if the semantics is big enough, it should override the syntax.
And it'll learn which bits of that vector are the semantics and which bits are the syntax, and it'll ignore the syntax.
Using subsets of dimensions, which you call bits, right, for different functions. It's just not clear to me it would. Maybe it would.
That would be
But
the rational
research,
way.
right? No, as in, I don't know if it would work at all,
Right.
right? I have
But it's
no-
a very good suggestion, yes. Because this is an amazing model, and one thing you can do is put it up against other character predictors like Markov ones. But these Markov character predictors, particularly ones that use a mixture of methods, are very good. And this is about as good as the best one, but makes very different errors. So one thing we're going to do is average this with the best Markov model, and I think we will get a better model, because those can't balance parens, for example. But this kind of thing is the way to really convince people.
This is on one GPU, sitting for a month. The stuff I'm talking about from the labs, they ran it on Roadrunner with, all banks going for a month, the biggest supercomputers in the world. So that you could even get anywhere close, and you have a result that you're trying to match. There's some possibilities to set up an experiment that would show how you can do this on commodity hardware, basically. That would be interesting.
Okay.